Okay, it seems that it started. So, now let's go back to our problem of, just to summarize very briefly, estimation of water resources availability through generation of synthetic data. And we are dealing with generation through probability theory. And I told you that this, we are working in the framework of stochastic processes. And the stochastic processes, just to remember, they are a collection of random variables. So for each observation time of our process, each time we observe the process, we basically have to identify a random variable to describe the process at that time. So if the process is river flows, as in our case is, at each time of observation of the process, we identify a random variable describing the river flow at that time. And the problem is to describe, with a statistical description, a probabilistic description, to describe the occurrence of this bunch of data, so a group of random variables, which have to be generated all together and not individually, because there is dependence, as I said. And the problem is that these random variables that we are trying to describe have a distribution that in general is varying, is arbitrary. So each time you have a different probability distribution. And these probability distributions need to be described through an analytical formulation at each time step. But we also have to describe their dependence. So how they succeed one after the other in time. And as I said, there is dependence because there is memory in the river. So this is a problem, indeed, because you can fully understand that it's already problematic to simulate just one random variable. You can imagine that it's more and more problematic to simulate all of them together, to represent all of them together. And I said that an idea would be, a possible solution would be, just one possible solution would be that we make a transformation of the process so that at each observation time we have one individual probability distribution, but these probability distributions are the same. They don't change. And besides not changing, they are independent. So this is a possible idea. Make a transformation to the process to make these probability distributions independent and identically distributed. D. This is a possible solution, not the only one. And if we succeed in doing that, of course, the problem becomes simpler because we still have to simulate a lot of probability distribution, but they are identical. Just 1 second, there is, as usual, the connection problem. If we don't resolve it, I will put the USB stick. So this is one possible solution. And if we apply this solution, we basically, one possibility to apply this solution is to adopt the theory of linear stochastic processes. And we will see what linear means. So this idea, this possible solution of making the probability distributions IID leads us to consider the theory of linear stochastic processes. And as I said, don't be concerned by the terms because the theory is, you will see, it's very simple. The problem is just to get into the framework of statistical analysis, which is something that in some cases it's not so easy to get. I just opened the page where I put my notes, and the notes were updated yesterday night, but I anticipate that I still have to work on them because they are not completed. So with my lecture, today's lecture, I will move beyond what is written here, but I'm planning to get online very soon. Just 1 second, I opened the page just to show you what is what's here. So and here we are linear stochastic processes. Okay. One important thing, because before I move forward, you should have clear in mind the distinction between the process and what we observe. So the process is the physical mechanism that is underlying what we see. So the process could be conservation of energy, conservation of mass. The process, if we adopt a statistical probabilistic representation, is the family of the random variables. So we rightly say the stochastic process is a family of random variables, is a collection of random variables. This is the mechanism which lies behind what we see. And then there is what we see, which is a time series, usually, of observations. A time series is a sequence of observations depending on time. You have to be fully aware of the difference, because one thing is the random process that generates several possible outcomes. One different thing is what you see, the time series, which is just one possible realization, is what we saw, what we observed. But it could have been something different. And keep in mind that what you see is not random. Once that you have observations, you have a time series. This is not random, because it's deterministic, it's a series of numbers. So you may say that there is uncertainty behind it, but uncertainty implies the fact that the mechanism is random. But once that you observe the process, it's not random anymore. Think of the elections. Before an election, you say, okay, it's random, of course, it's a random process, because you can't deterministically predict the outcome from an election. But once that you saw the results, it's not random, it's a fact. So you have to have clear the difference, because it's not clear in the literature. So sometimes you see that a time series is a random process. No, a time series is not a random process. A time series is a collection of observations along time. It's the process that generated their time series that may be random. And you have to be fully aware of the difference, because it's extremely important. We cannot say that once we observe the river flow, it's random. It's not random, it's observed. Okay. And as I said, this is not clear in the literature. Even in books, in textbooks, it's not clear. But it's extremely important that we see the difference. One thing is, the physics, and the other thing is the result of that. Okay, so linear stochastic processes. As I said, it's very simple. The question is, can we apply to our process, which is river flow, and it's a random process, can we apply a series of transformations to make the process composed by IID random variables? And if we look at the time series, which is just one realization of the process, can we apply to the time series a series of transformations to make each observation behaving as they were generated by independent and identically distributed distributions? This is the question. Of course, we can understand that at the beginning, the process, and let me also add the Gaussian distribution. So the distribution I also require, besides being identically distributed, the data, I also require that they are Gaussian, and I will tell you why. It's very simple, but let me just tell you in 10 minutes from now. Look, we know that the data are dependent. The process, the data, also the time series, there is dependence, we will see how to quantify it. Also, the process is dependent. We know that the process in general is non-Gaussian. So we know that this condition is not satisfied at the beginning. We know that the process is non-Gaussian. And also we know that the process is generated by variables that are diversely distributed. Because think of river flows in November, for instance, in our climate, Po River, and think of river flows in August. It's clear that the probability distribution is different. Think at the mean flow. If you look at the Po River, the mean flow in August is 600 cubic meters per second. If you look at the mean flow in November, it's 1,000 cubic meters per second. And this is just the average. So if the average is different, it's clear that the probability distribution is different. So it's clear that these random variables are non-Gaussian, are dependent, are not identically distributed. So let's think about, by thinking at the physics of the process, what we can do. First of all, the variables are non-Gaussian. Let's start from this. And first question, is it true that they are non-Gaussian? Yes, it's true. Because if we think at hydrological variables, I already mentioned to you that only in a few cases they are Gaussian, and only if they are observed at very large time step. We already talked about this. I told you that any random variable, if you average it over a long time step, then it becomes Gaussian. But if the time step is fine, like in our case, let's suppose that we deal with daily data, they are non-Gaussian. So first question, can we make them Gaussian? Yes, there is this transformation which is frequently applied to make the data Gaussian, and the transformation is very simple. We can take the logarithm. Let's suppose that our process is represented by the river flow depending on time. And let me indicate with this the random variables. Okay? And if we take the logarithm of Q, it's a very simple transformation. We can take it because river flows, as well as many hydrological variables, they are positive. So we can compute the logarithm. What is the effect of computing the logarithm? You know, the peaks are kind of smoothed down because the logarithm is a transformation that on small numbers is less impacting than for high numbers. So in our case, what is the origin of non-Gaussianity? The origin is the fact that in some month you have the river flows that have a higher magnitude with respect to the drought months. So if you take the logarithm, on the drought you don't reduce much. You reduce, of course, the droughts, but in percentage terms you don't reduce them much. If you instead compute the logarithm on the high flows, you reduce them a lot in percentage terms. So it can be proved, and we can also try with R. It's very simple. We can prove that the logarithm is quite effective in making the data Gaussian. This is what it's usually done. And it works quite well if you observe the data at a time step that is not much fine, because the finer the time step, and the more the data is far from Gaussian. As I said, if you enlarge the time step, you get closer to Gaussianity. If you reduce the time step, you get far from Gaussianity. So if you deal with daily data, the usual experience for daily river flow data is that if you take the logarithm, they become closer to Gaussian. Now you should have a question, how can I check this? How can I check if it was effective, this transformation? There are several techniques. One possibility is that you visualize the probability distribution of the data. And you know, this is extremely simple to do in R. So let's suppose, for instance, let's get the time series of the Po River. Let me start an R window. And just 1 second, let me start it from a different directory. And let me try to get back the time series of the Po River. And I don't remember what is the name, sorry. I think it's try with this. This is this is the time series of the daily flows of the Po River at Piacenza. I'm just visualizing a plot. And this is the time series. These are daily flows of the Po River at Piacenza. I don't remember the observation period, but it's somehow 60 years between, I think, 1950 and 2010. And it's a bit more than 50 because it's 80, I would say 80 years, but the observation period is up to now, up to a few years ago, and it started about 1940, something like that. Anyway, it's not really important. You see the river flows, they are in cubic meters per second, and you can see clearly here that there are variations, changes of the probability distribution. It's not so easy to see here because, of course, the graph is very squeezed, but you can see the effect, for instance, of the seasonal variations. It's clear there is a kind of harmonic behind it. But let's look at the probability distribution of the data. It's very simple to compute it, and we can just write plot density of the time series. And the density, let's put a type equal line. And in this way, we get the probability density. And probability density, remember the difference between probability or cumulative probability and the density. So you see the density, and it's clearly non-Gaussian. Because if you remember when we spoke about probability theory, we said that the Gaussian distribution is symmetric, which means that it's described by a bell, which is symmetric around the mean. Here you see that the mean is somewhere around here. I would say that it's probably more or less, probably it's around 500, 600 cubic meters per second, and then you see a long queue. So we say that the river flows are long-tailed. You see the long tail, sorry, not a long queue, a long tail. And of course there is a long tail because the river flows are limited to 0. The lower level is 0, the upper level instead is very high. So of course you have a long tail because you have a small probability of occurrence of very high flows, which are the floods. And you see clearly that the density is not symmetric, it's clearly not Gaussian. Let's now try to take the logarithm. And it's very simple, just put a ln here. Sorry, it's not ln, but it's log. And let's look at the distribution. You see, it's much closer to Gaussian. I can see that it's still not Gaussian, because if you try to play with R, I show you the density of a Gaussian distribution with the same number of data, 30,000. If I plot the density of this, which is R norm is the R function to generate Gaussian data, and let's generate with mean 0 and standard deviation 1. So it just suffices that I put the number of the data to be generated, and this is the Gaussian distribution. You see that with respect to the other one, which I will plot soon, it's what is the difference? Is symmetric, more or less. It's not really perfectly symmetric. Why is that? Because it's computed on the data. It's not derived from the process. From the process, it would look like perfectly symmetric. This is derived from the data, so there is, of course, uncertainty. But still, we can see that it's symmetric, indeed. And you see the tails, they are short. And it's very compact. The Gaussian distribution has this nice behavior. It's compact. It doesn't have many outliers. If I look now to the distribution of the logarithm of the Po River, you see that the tails, you see that it's less symmetric, and the tails are longer. But still, you see the results. It's amazing. With a very simple transformation, I got very close to Gaussian. And I mean, we don't need to get strictly Gaussian. It's written in my notes. You don't have to be so rigorous. For technical applications, it's not necessary that, you know, we want the maximum of the precision. So I think that this result is fine, for instance. And there are also statistical tests that you can apply in order to check if the data are Gaussian. And I would say that you don't really need them unless you have specific requirements. Because sometimes, you know, I accepted an approximation even if the statistical tests were not strictly speaking satisfied, because, as I said, for technical applications we don't really need to be so rigorous. But there are statistical tests, and in my notes I put some links to the description of some tests, because they are indeed very simple. They are not difficult. Usually when I write scientific papers on that, the referees are not happy with just a graphical check. They want a rigorous check, because, you know, when in the scientific context they are more rigorous. And then in the papers usually I put the statistical tests. They are very simple. Maybe that they are not satisfied, but still it's important in some cases that you perform them, and then even if they are not satisfied, you say, okay, but I keep moving forward anyway for the technical applications, but on the basis of a more rigorous check. But anyway, I would say that in this case it's fine. So basically the first problem, it seems that it's solved. So the data are Gaussian. Still they are not identically distributed and not independent. There is one thing to say which is described here. What I did check is the probability distribution of the whole bunch of data. And you know, the data come from just one outcome from the process. Indeed, it's not just enough, it's not required that the whole data are Gaussian. The requirement is that the data at each time step are Gaussian. And if they are Gaussian at each time step, then when you put them together, the whole group is Gaussian. If you compose, if you sum Gaussian distribution, you put them together, the result is still Gaussian. So but the opposite is not true. If we check that the whole bunch of data is Gaussian, we cannot say that then the data at each time step come from a Gaussian distribution. And it's very difficult to check at each time step, because you need a lot of years of observations. You could check it by taking the time series of each year, looking at, for instance, looking at what happened in the 1st of January each year, and see if all the data observed on the 1st of January are Gaussian, 2 of January are Gaussian, etc., etc. But this is indeed very complicated, and usually we don't have enough data to do that. But still, I'm mentioning to you this problem because when we look at the final result, at the final technical result of these methods, of course we want the synthetic series be reliable, and in some cases we see that it's not. And one of the reasons is that the data as a whole are made Gaussian by the logarithmic transformation, but not the individual random variables. And I realized that because this is something that you don't find in the books. I realized that because in some cases I got really mad in trying to, you know, I got the results and then the results were not really satisfying. And what's the reason? I made all the statistical tests, it seems that everything went fine, so what is the reason? And then by really making a lot of experiments, I understood that the problem was that the data are made Gaussian by the logarithmic transformation, but not the individual random variables. I hope that the problem is clear to you. I just want to mention this because it's important from a technical level, because at the end of this lecture, I will tell you how to check that the simulation is reliable. And if we try, for instance, with the Po River to generate data, it's not easy. And one of the reasons is what I'm talking about. But okay, let's assume that we got to a Gaussian distribution at each time step. Now, still we are not to target because we still have dependence and we still have changes in the probability distribution. Let's assume that it's Gaussian, but the Gaussian distribution has two parameters, as you know. And the two parameters are the mean value and the standard deviation. And if we look at each time step, we see that the data, they are Gaussian after the transformation, let's assume that, but still the mean is different. If you look at the data, for instance, let's have a look at this data for the Po River, at the logarithm. Let me plot it. And the plot is here, let me see, here. So let's plot the logarithm now. And you see that the mean value, you see that you still see the harmonics, you still see the periodicity, you still see the seasonality. So next step, let's make the mean of the data flat. It's not the case now. For instance, if I plot the first year of data, 1, 2, 3, 6, 5, you see that it's not very clear here, the seasonal component, because this was a year with not many peaks, but still you can see autumn, you see that there is a peak. And in many of the other years, you will see also the peak around here, June. Here it's not really clear, because there was also an high flow at the end of the summer. So, next step, let's make the data flat, and this is what we call deseasonalization. So, we look at the physical process. Also, we look at the time series, but we also reason on the physical process. We understand that the process is what we call seasonal, which means periodic, which means that the average value is fluctuating along the year, along the seasonal cycle, and probably also the standard deviation is fluctuating. You know, the logarithmic transformation also stabilizes the variance, the variability. But still, I'm sure that if we look at the variability of this data along the year, there are changes. So deseasonalization is in charge of stabilizing the mean of the random variables, I mean, along the year, and stabilizing the variability. How we can do it? It's very simple. It's extremely simple. What happens here? It happens that if we look at the seasonal cycle, so if we look at the period between January 1st and December 31st, we see changes in the mean value. And you know, you can clearly see this because if you have a lot of years of observations, you could compute the average value in each day of the year. So if, like in this case, you have 60, 70 years of observations, if you take all the data collected on the 1st of January, you can compute the average, the mean. And you can see that if you plot these means, these averages, one after the other, from January 1st to December 31st, you can clearly see something like this. So let's indicate this mean value with the symbol μj, where 1 is, where j varies from 1 to 365. And let's plot it against j from 1 to 365. Let's forget about February 29th. The leap years, the observations from January 29 are removed, okay, because it's a singular, you can remove them. This is what we usually do. Before starting, we remove any observation on February 29. So, if you plot it for the Po River, maybe that by playing a bit, we can do that. You see that you start from a value like here, you see an increase and then you see a minimum, and then again an increase, and then back to this value here. This is what you see. So clearly, what is this again? Is the average value of the observations collected in each J, which is day of the year. Okay? So how can we compute this? It's extremely simple. We need to put the data in a table where we have here the years. And so, for instance, 1940, 2010. And here we have the days, days from January 1st to December 31st. And then here you have your numbers. For every year. And then here you compute the average. Which is me, J. And then here you have your average, which is plotted here. It's very simple. Now, these average values are different, so how can we stabilize them? But it's very simple. From each observation, we just have to subtract the corresponding average. And then the average value becomes flat. So in mathematical terms, let me write here. Let's identify each observation with the symbol Q, T, J, where T is a progressive index, progressive time index. And J is the day of the year. Okay, so instead of saying just QT, where T is a progressive time index, let me introduce a second index which identifies the day of the year. So T varies from 1 to 30,000, like in that case. J varies from 1 to 365. Okay, and then we can write the transformation in this way. QD Tj, it's equal to Q Tj minus me J. Let me put J between parentheses. Here it was as a subscript. Let me be consistent also with my notes. Now we can also write an expression for μj, which is the average value. Let me delete this column here. The average value for each day. Basically, we can write that μj is equal to the summation for t equal 1 to n of Q T. Let me say Qt. Here I need to introduce another index I, where I equal j. Let me write here. So I take the sum of all the data for which the second index is equal to the given j. So let's suppose that j is 1, January 1st. I take the summation of all the data over the whole bunch of time step t for which the second index is 1. And then I divide the summation by the number. Let me indicate with okay, let me indicate with n of Q T I equal j. So the summation of all the data for which I is equal to j divided by the number n of the data for which I is equal to j. And let me use n in this case as a function indicating the number of the data observed on the 1st of January. Okay, so let's suppose that j is 1. This becomes μ1, which is the mean of the data observed on the 1st of January. And this is the summation of, for t equal 1 to n, of q t 1 divided by n q t 1. So you take the sum of all the data for which the second index is 1